All right, today's topic is electric current. This is where electricity gets more familiar, although I'll do my best to try to confuse you as much as I can. um, and there's something to that because electric current, though it seems pretty basic, is actually at the quantum level is pretty confusing. So I'll try to point out the confusion without actually confusing you. So electric current, they use a water analogy, but instead of current being the flow of water through a pipe or down a river, it's the flow of electric charge. And it's our job to figure out what exactly does that mean. So it only occurs when there's a potential difference across the ends of the conductor. So if you have a wire hooked up to a battery, then current can flow. But if the battery's dead, if there's not a potential difference across the positive and negative poles of the battery, then there won't be any flow. Just as if this water level was the same on both sides, there would be no flow. And if water is allowed to flow, it will flow from high pressure to low pressure until the pressures equalize. Okay. So similarly, if you have a pump, you can cause the flow to be continuous. Just like with a generator, if you have a generator, you can cause the flow of current to be continuous. Okay, so electric charge. Sometimes when you hear people talking, they'll talk about current as being the flow of electrons, which isn't exactly right. The electrons produce the charge, but the electrons are not the charge. It's the charge that flows, not the electrons per se. The units of current are amps. You've all heard of amps, named after Ampere, a French physicist who did early studies in electricity. An amp is defined as 1 coulomb of charge per second. And that's the amount of charge produced by a whole lot of electrons. That many electrons. Okay. So current, amperage, is caused by electric pressure, which is the voltage. Just as water flow is caused by water pressure, electricity flow, the flow of charge, is caused by electric pressure or voltage. So voltage produces amperage. So think of voltage as electric pressure due to a difference in electric potentials. And we talked about electric potentials in the last unit. So voltage sources are things that provide a potential difference, whether the potential difference is chemically induced, like in a battery, or whether it's physically produced, like in a generator. And we'll talk about how generators work in a couple of chapters. Okay, so dry cell batteries, which aren't really dry. In fact, they cease working when they dry out, uh, but they're just kind of moist. They're not truly wet. So batteries that are sealed up that you can't recharge are called dry cells. Wet cell batteries are like your car batteries, and they're called wet cells because there's actually liquid in there. It's a sulfuric acid or some other strong acid, and they can be recharged. Generators, um, which are diagrammed here. So in generators, regardless of the kind of generator, you have magnets and coils, and you either have to move the magnet relative to the coils or move the coils relative to the magnets, and they generate electricity that way. So when you see wind turbines, it's basically a big giant generator, which is pushed by the flow of wind. Okay. In fact, all electrical power plants, except for truly solar power plants, um, use generators. So in this case, you have water flowing in hydroelectric power. You have water flowing that moves the turbines, which are attached to the generator in the power plant, which produce the electric current. You have coal-fired power plants, which burn coal to heat up water to produce steam, which drives the generator. Even nuclear power uses nuclear energy to heat water to produce steam to drive the generator. Okay. Oops, I went backwards. So the nuclear power is over here. So voltage sources. They are numerous. Hopefully we'll get better at not using this or this and just learn how to use direct solar power. Okay, so how are they related? How are current and voltage related? Now, applied voltage, or the electric pressure across a circuit, and we'll talk about circuits in the next chapter, causes a current to flow. And remember, the current is the flow of charge. So voltage, the electric pressure, causes current, which is the flow of charge. Now, there's a third property involved in circuits and electric current, and that is resistance. So the resistance that a conductor provides to the flow of charge is electric resistance. So you can think of it as kind of like electrical friction. So just as if in a pipe, if you have like a corroded pipe, the corrosion will slow down the flow of current. And similarly, different conductors have a higher or lower resistance. So there are four properties that affect the resistance of a conductor. The overall conductivity, which is based on the properties of the material, the thickness of the conductor, the length of the conductor, and the temperature of the conductor. So the more conductive the material, the lower the resistance. So things that are superconductive, like silver and gold, don't heat up very much as current flows through it, and things that are less conductive have a higher resistance. The thicker the wire, the lower the resistance. So if you have a little tiny thin wire and you're trying to run a lot of current through it, it's going to get really hot. The shorter the wire, the lower the resistance. So if you have a super long extension cord and you're trying to run something that draws a lot of current, like say a drill motor or something, it's not going to run as fast, and the wire will heat up. And then the lower the temperature, the lower the resistance. Except in carbon, there the higher the temperature, the lower the resistance. Okay, so the units of resistance are ohms, and this is where I like to introduce a little bit of humor, and there's actually an extra credit assignment that you can do. If you come up with a kind of a pun like this, Coulomb, ohm, and he's cool. Some kind of a joke related to electricity, ohm. So if you come up with or share with the class any electrical dumb joke, then you can have some extra credit points. Okay, so a resistor is any device that allows electric current to flow through it. It can be a light bulb, it can be an appliance, or it can be an actual device that they put into the circuit to control the amount of current. So if you have house current, that's going to run a certain device, but that amount of current would actually be too much for it, then you put a resistor in the circuit to only allow a smaller amount of current to flow through it. Okay. Now, Ohm's law is the law that relates these three properties together: current, voltage, and resistance. So if you think about the amount of current, it's directly proportional to the voltage. So if you have more current, it's going to require a greater voltage to push it. But it's inversely proportional to the resistance. So the greater the resistance, the lower the current, if the voltage stays the same. So if you remember, amperage is the units of current, volts are the units of voltage, and ohms are the units of resistance. Now, the original form of Ohm's law is V equals IR, easy to remember, where V is the voltage, I is the current, and R is the resistance. You'll be given 3 out of the 4, or be able to, 2 out of the 3, or be able to find 2 out of the 3, and then you just solve for what you don't know. So this would be this version, and then if you want to solve for R, it's V over I. Okay. So keep in mind as you are doing current problems that voltage supplies the push, resistance opposes the push, and current results. Okay, so that's it for part one. The next